In the previous lecture, we have seen the concept of solution of second order differential equation with variable coefficient when x equal to 0 is an ordinary point of the given equation. Now today we are going to discuss some of the important problems so that the idea developed in the previous lecture will be clear to you. In fact, I am considering here two problems and we will solve it by the method of Frobenius developed to solve such problems. So you can see the first example. The first example says that we have to solve in series the differential equation 1 plus x square y double prime plus xy prime minus y equal to 0. So here you can see if we compare this given equation with the standard form of the equation which we have studied in previous lecture, that here p naught of x, when you say p naught of x, it means this is the coefficient of y double prime, and you can see this is 1 plus x square, and if it is 1 plus x square, then you can see that if x is equal to 0, then p naught 0 is equal to 1 plus 0, and this is equal to 1, and so it is not 0. And if it is not 0, then you know that this particular point x equal to 0 is called an ordinary point of this equation. Although here p1 of x is x, which is also variable, p2 of x is equal to minus 1. So since x equal to 0 is an ordinary point of this given equation, which have been defined here, 1 plus x square plus y double prime plus xy prime minus y equal to 0. So we know in this condition we will write the solution of this equation in this series y equal to a naught plus a1x plus a2x square plus so on plus an x to the power n plus so on, and in compact form by the use of summation you can write it as summation k from 0 to infinity ak x to the power k. So this is its series solution, but you know we do not know the value of a naught, a1, a2, a3 and so on. So our aim is not to evaluate the values of the coefficients a2, a3, a4 and so on in terms of a naught and a1, because you know this is a second order differential equation. So definitely in its solution there must be two arbitrary constants. So here in fact these a naught and a1 are the arbitrary constants in terms of which we will find the other coefficients and then we will get the actual solution of this equation. And you know, for this, first of all we will differentiate this equation 2 and get the value of y prime and y double prime, and then we will substitute those values in equation 1, and after simplification we will get the values of the coefficients like a2, a3, a4 and so on. So let us do it. So you can see what will be the value of y prime. When you say y prime, it means this is dy dx, and you can see this equation number 2. From here we will find actually dy by dx, and this will be simply equal to summation over k ak x to the power k minus 1. And since you can see here that if we will put the limit k equal to 0, then due to this k, this term will vanish. So there is no need to write the limit 0. So we will start the value of k from 1, and so k will run from 1 to infinity. And then we will find y double prime. Y double prime it means d2y by dx square. And when you write d2y by dx square, it means this is d dx dy by dx. And dy by dx has already been found here. So again differentiate this and then you will get y double prime. So this will be summation over k into k minus 1 into ak into x to the power k minus 2. Simple formula of x to the power n differentiation has been used here. And now you can see, if we will put k equal to 0, this term will be 0. If you will put k equal to 1, then again it will be 0, because 1 minus 1 will be 0. So here there is no need to write the limits 0 and 1. So we will start the limits for k from 2. So here k runs from 2 to infinity. So these are the values of y prime and y double prime. Now we will substitute the values of y double prime and y double prime in that equation 2. So substituting for y prime and y double prime in equation 2, we get, when we will substitute this in this equation number 2, what we will get? You can see the equation is sorry, not in equation 2 but in equation 1. In equation 1. So what will be the result? You can see this will be 1 plus x square. This is the coefficient of first term, and summation k equal to 2 to infinity and k into k minus 1. Here is d2y by dx square and it has been found here. So this is k into k minus 1 ak x to the power k minus 2 and plus x dy by dx, and value of dy by dx we have obtained here. So this is x summation over k from 1 to infinity k into ak into x to the power k minus 1, and minus there is simply y, and y you have seen here that we have defined this y as it defined in this equation 2. So at the place of y we will write summation k from 0 to infinity ak x to the power k, and this equal to 0. Now we will expand this summation to some of the finite terms, and so you can see that this equation may be written as 1 plus x square into, when you will put k equal to 2 in this first term, what will be the result? 2 into 2 minus 1, that is 1, into ak, and x to the power 2 minus 2, that will be simply 0, and plus, now let us put k equal to 3. So our result will be 3 into 3 minus 1, that is 2, into ak means, sorry, here ak means in the first term ak will be equal to a2. we have to put k equal to 2 here. So this is A2, and 3 into 2 into k is 3, so this is A3 into x to the power 3 minus 2, that will be equal to 1, and plus so on, and plus, let us take k equal to n. So this will be n into n minus 1 into an into x to the power n minus 2. Now let us put k equal to n plus 1. So this will be n plus 1 into n into a n plus 1 into x to the power k minus 2, and k we have assumed n plus 1, so this will be x to the power n minus 1, and plus, if we put k equal to n plus 2, then this will be n plus 2 into n plus 1 into x to the power n, and plus so on. In fact, for convenience, we have written the terms up to x to the power n. And now we will expand the second term here. You can see when we will actually expand this second term, taking the limits k from 1 to infinity, what will be this expansion? You can see. So this will be plus x into a1 plus 2a2x, you can see, and plus so on, plus n x to the power n minus 1, and plus so on. And now finally we will expand the last term, and the last term's expansion will be simply a0 plus a1x plus a2x square plus so on plus an x to the power n plus so on. So we have substituted the values of y prime and y double prime in the equation 1, and also expanded to some of the terms. Now actually we will arrange these terms by taking all those terms having the same power of x. So let us arrange this term. So you can see, if we associate all the terms in which there is x to the power 0. So here x to the power 0 is present, and its coefficient is 2a2, and in here you can see in this second series there is no x to the power 0, but in the third series there is a0 only, so it means it is a0 into x to the power 0. So this will be associated with this term. So this will be 2a2 minus a0 into x to the power 0. So this is 2a2 minus a0 into x to the power 0. Although there is no need to write x to the power 0 because it is simply 1, and plus. Now we will see the coefficients of x to the power 1. So here coefficient of x to the power 1 is 6a3, and in this second series it is in fact a1, and in third series it is also a1. So this a1 here and this a1 here will cancel out because it is plus here and here it is minus. So only one term remains, which is 6a3. So you can write it, this is plus 6a3x and plus so on and plus. Now we will associate all those terms in which x to the power n is present, and you can see from here, here actually when we will consider this 1 into this much, 1 into this much, then 1 into n plus 1 n a n plus 1 x. So see, first of all, this when you will actually multiply this term, yes, when we will take 1 into, in fact, this much, then there will be x to the power n, and when we will take 1 into not here, here will be only one term, and here when we will multiply this x to this term, then again there will be x to the power n, and here is already x to the power n. So considering all the terms containing x to the power n and associating them, we will get n plus 1 into n plus 2 into a n minus 2 and plus n into n minus 1 into a n plus n into a n minus a n and into x to the power n and plus so on. This will be equal to 0. So let us simplify these terms to some extent. You can see that this will be 2a naught minus minus a naught minus a naught into x to the power 0, and there is no need to write this x to the power 0 here. So you can write simply 2a2 minus a naught and plus 6a3 into x and plus so on and plus n plus 1 into n plus 2 into a n plus 2. Here is plus 2. So this is n plus 2. N plus 2. And plus, when you will write this term, this will be n square minus n, and so an minus an into n and plus an into n. This will cancel out, and we will associate this term and this term. Then we will get n square minus 1 into an into x to the power n, and this will be equal to 0. Now this is an identity, so if it is equal to 0, definitely the coefficient of each powers of x will be separately equal to 0. So now we will equate to 0 the various powers of x. So equating to 0 the various powers of x. Let us see here. Actually this 2a2 minus a0 is the coefficient of x to the power 0. So we will write 2a2 minus a0 equal to 0. And from here you can see that this 2a2 is equal to a0, and so this implies a2 will be equal to a0 over 2. Now we will equate the coefficient of x to 0. So what will be the result? This will be 6a3 equal to 0, and this implies a3 is simply equal to 0. Again, in fact, we take the general term, and you can see that the coefficient of x to the power n is what? Coefficient of x to the power n is n plus 1 into n plus 2 into an plus 2, and plus n square minus 1 into an. So we will actually equate these terms equal to 0. So here will be x to the power n. So now n plus 1 into n plus 2 into an plus 2, and plus n square minus 1 into an, and this equal to 0. And from here you can get an plus 2, you can see, is equal to what? This will be minus n minus 1 over n plus 2 into an. Let us see that this relation is actually known as a recurrence relation, as I have told you when we will actually dealing with the general method or general technique to solve such problems. So this is a recurrence relation. This is a recurrence relation, or you may also call it recurrence formula. So now from this recurrence formula we can find the values of a2, a3, a4 and so on, simply substituting the appropriate value of n here. So you can see, if you want to find the value of a3, you should take this n equal to, in fact, n equal to 1. So now we know that we have to find the values of these coefficients in terms of a0 and a1. So when actually we have to find these values, we will substitute the value of n equal to 2, 3, 4, 5 and so on. So putting n equal to 2, 3, 4, 5 and so on in equation 3, what will be the result? When we will put n equal to 2 here, then this will be a2 plus 2, that is 4, and in RHS you can see we have taken n equal to 2, so this will be 2 minus 1 over 2 plus 1 into an, and n we have taken 2, so this is a2. This is a2, and so this will be minus, n has been taken 2, and so this will be, see, n plus, actually here is n plus 2, so we should write here 2. So 2 plus 2, that will be 4. So this is minus 1 over 4 into A2. But we have seen that this A2 is what? You can see A2 is A naught by 2. So let us put A naught by 2 at the place of A2. And so this will be equal to minus 1 over 4 into A2 is A naught by 2. So this is minus 1 by 8 into A naught. So this is the value of A4. Now find the value of A5. For that you can put here n equal to 3. So when we will put n equal to 3, this will be A5, and what will be the result? You can see minus, we have taken n equal to 3, so this will be 3 minus 1 over 3 plus 2 into an, and n is 3, so this is in fact A3. So what is this? This is minus 2 over 5 into A3. But you have seen that this A3 is actually equal to 0. So this A3 is 0, and so this result will be 0. So A5 is 0. Now let us put n equal to 4. When we will put n equal to 4, the coefficient will be A6. And what will be this? You can see I have taken n equal to 4. So this is minus 4 minus 1 over 4 plus 2 into A4. And this will be minus 3 over 6 into A4. And you have already found the value of A4, which is minus 1 over 8 A naught. So this is minus 1 over 8 A naught. So after simplification, you will get that this is in fact A naught by 16. A naught by 16. Here actually this 3 and will cancel out, and minus minus will be plus. So this is A naught by 16. And similarly, you can get the value of A7. A7 means we will take this n equal to 5, and then when you will take n equal to 5, you will get this is minus, I am writing directly here, you can see it, minus 4 by 7 A5. And as A5 you have found equal to 0, so this will be 0. So actually all the coefficients having the odd subscripts, that is A3, A5, A7, A9, all will be 0. And the coefficients with the even subscript, that is A2, A4, A6, A8, these will be non-zero. So similarly, we find some of the values too. So you can see from here that this A8 will be equal to minus 5 by 8 A6, and we have already found the value of A6. So after substituting the value of A6, you will get this is minus 5 A naught divided by 128, and so on. In this manner you can find all the coefficients. So now we have obtained the values of different coefficients. So now we will substitute these values of coefficients in equation number 2, and after substituting these values we will get the solution of the given equation. So now substituting the values these values, you can say these values in equation 2, we get what we will get. You know what is this equation 2? Equation 2 is a naught plus a1x plus a2x square plus a3x cube plus so on. So if we will write the values of a2, a3 and so on, what will be our result? You have to put a0 and a1 directly, because we have obtained these values in terms of in fact a0 and a1. So this is a0 plus a1x plus a2, you have found this is a0 by 2, so this is a0 by 2 x square, and a3 you have obtained its value in fact 0, so this term will vanish, a3 will be 0, so we will now write actually the a4x4 and so on. And you know the value of a4 is what? This is in fact you can see here the value of a4 is minus a0 by 8. So this will be minus a0 by 8 into x to the power 4. Then again a5, the term containing a5 will be 0. Then we will have to put a to the power, a6, and in this manner you will get that this is a0 by 16 x to the power 6, and again minus 5a0 divided by 128 into x to the power 8, and so on and so on. So you can see that if we take this a0 as a common factor, then except a1x, in all terms a0 is present. So except this term a1x, you can associate all the terms taking this a0 as a common factor, and this will be a0 into 1 plus 1 over 2x square minus 1 over 8 x4 minus 1 over 16 x to the power 6 minus 1 over 16 is actually plus, and this is 5 over 128 into x to the power 8 and plus so on. So this is actually the required general solution of the given equation, and you can see, there is one term remaining here, so you can write this is plus a1x. So this is the required solution, and you can easily see that this solution actually contains two arbitrary constants. First one is a0 and another is a1. So this should be here because this is equation of second order, and so there must be two arbitrary constants in its solution. So this is the required solution of the given equation. Now we will see the solution of the second equation, which actually I have mentioned here. This is y double prime plus x square y equal to 0. So now let us see the solution of that equation. Number 2. The given equation is given differential equation is, what is the given differential equation? This is y double prime plus x square y equal to 0. This is our given equation. Again, you can see this in this given equation, the coefficient of y double prime is in fact 1. So here you can see, if we compare this given equation with the standard equation, which you know, this is p naught of x y double prime plus p1 of x y prime plus p2 of x y equal to 0. This is our standard equation. So comparing with this standard equation, you can find that this coefficient p naught of x in the given equation is actually equal to 1. So here p naught of x is equal to 1. And if p naught of x is equal to 1, then what will be p naught of 0? When you say p naught of 0, it means you are taking x equal to 0. So you can see this is independent of x. So this will be actually equal to 1. And if it is 1, it means it is not 0. So we can say that x equal to 0 is an ordinary point of this given equation 1. So x equal to 0 is an ordinary point of equation 1. And if x equal to 0 is its ordinary point, then you know the solution of this equation will be written in a series of particular manner, which we have just used. So therefore solution of equation 1 is given as, we will write its solution in this form: y equal to a naught plus a1x plus a2x square plus so on plus an x to the power n plus so on. And in compact form, we will write it summation k 0 to infinity ak x to the power k. Now, as you have seen, first of all, we will find these derivatives y double prime. Here there is no need of y prime actually, but for finding y double prime, you have to first of all find y prime. So you can see y prime means dy by dx. And what will be this dy by dx? From here you can see this will be summation k1 to infinity. You have seen that there is no need to put the value k equal to 0 because term becomes 0. So this k1 to infinity k into ak x to the power k minus 1. And when we will find y double prime, then again we will differentiate it, and the result will be summation k2 to infinity k into k minus 1 into ak and x to the power k minus 2. So now let us put the value of y defined in equation 2 and value of y double prime defined here in this equation 1. So substituting these values of y and y double prime in equation 1, what actually we will get? So substituting y and y double prime in equation 1. in equation 1. You can see in equation 1 actually the first term is y double prime. So we will simply put summation k 2 to infinity k into k minus 1 into ak x to the power k minus 2 and plus the second term of this equation is, you can see here, this is x square into y. So in this value of y, we have to multiply x square. So this will be x square into y, and instead of y, now we will write summation k 0 to infinity ak x to the power k, and this will be equal to 0. Now we will expand these terms, first and second term both will be expanded, and you can see that if we take k equal to 2, so this will be 2 into 1 into a2, and x to the power 2 minus 2, it means x to the power 0, and plus now we will take k equal to 3. So this will be 3 into 3 minus 1, that is 2 into a3, and x to the power here 3 minus 2, and that will be simply x, and plus so on and plus. Now let us take this value of this k as n plus 2. So this will be n plus 2 into n plus 2 minus 1. So that will be simply n plus 1. And ak, k is n plus 2. So this will be a n plus 2. And x to the power k minus 2. So n plus 2 minus 2. That will be simply x to the power n. And plus so on and plus. Now we will expand this term. So you can see this is x square into, this will be simply a naught plus a1x plus a2x square plus so on and plus. If you take this k equal to, in fact k equal to n minus 2, then this will be a n minus 2 into x to the power n minus 2 and plus so on. Here I have selected k equal to n minus 2, then x to the power n minus 2. So when you will multiply with this x square, then you will get x to the power n. So in fact, to get the term containing x to the power n, I have selected this particular value here for simplicity. So and this will be equal to 0. Now again, what we will do, now we will actually equate to 0 the different coefficients of different coefficients of various powers of x. So equating to 0, the coefficients of various powers of x, what we will actually get, you can see, in fact x to the power 0 is contained only in the first series. In this series actually there is no term containing x to the power 0. So coefficient of x to the power 0 is simply 2a2. So you can see this will be 2a2 equal to 0. And if 2a2 is 0, what does it mean? It means a2 is equal to 0. And again, you can see x to the power 1 is here in the first series, but in second series there will be no term containing x, because the lowest power term will be x square. So we can again put this 6a3 equal to 0, and so a3 is also equal to 0 here, and so on. In this manner you can get the values of the other coefficients. But we actually find first of all the recurrence relation for the nth term, and then from that recurrence relation we are able to find the various coefficients. So now let us think about the recurrence relation, and for that we will actually equate to 0 the coefficient of the term containing x to the power n. So you can see here in the first series, this is the coefficient of x to the power n. This is n plus 2 into n plus 1 into a n plus 2. And in second series, you can see when you will multiply this x square to this term, there will be x to the power n. So in second series, the coefficient of x to the power n is a n minus 2. So you can see what will be the coefficient of x to the power n. So this is simply n plus 2 into n plus 1 into a n plus 2 and plus a n minus 2, and this equal to 0. And from here we can get this a n plus 2 is equal to what? This will be simply minus a n minus 2 and divided by n plus 2 into n plus 1. This relation is known as a recurrence relation. This is a recurrence relation. And now substituting the values of different values of n, you can find the values of different coefficients. So here we will substitute, putting n equal to 2, 3, 4, 5 and so on in equation 3. In this equation we will substitute these values, and after that we will get, when you will put n equal to 2, see here, n equal to 2 means this is a2 plus 2, that is a4. So a4 will be what? I have taken n equal to 2, so this will be equal to minus a 2 minus 2, a n minus 2, and n is 2, so this will be simply a naught, and divided by, I have taken n equal to 2, so this is 2 plus 2, that is 4, and n plus 1, that is 2 plus 1, 3. So this is simply 3 into 4. And again write a5. When it will be a5? When we will take actually n equal to 3. So this will be, you can see, if n is 3 here, a3 minus 1, that will be a1. So this is minus a1 and divided by 3 plus 2, that will be 5, and 3 plus 1, that will be 4. So this is 4 into 5. And similarly a6, when a6 will be obtained? When we will actually take n equal to 4. So here will be a4 plus 2, that is a6, and in RHS you can see, since n has been taken as 4, so this will be a4 minus 2, that is a2. So this is a2 over 4 plus 2 6 and 4 plus 1 5. So this is 5 into 6. And since we have seen that actually this A2 is what? You can see here. Since A2 is 0 and A3 is also 0. So since A2 is 0, so this result will be 0. It means A6 is equal to 0. In fact, in the similar manner, when you will obtain the value of A7, you will find that it is 0. When you will obtain, because you can see what will be the value of A7, let us clarify it. A7, I am finding its value. You can see when you will find A7, it means we are taking n equal to 5. So here will be minus A, 5 minus 2, that will be 3. So this is A3. And divided by n, 5 plus 2, 7, 5 plus 1, 6. So this is 6 into 7. And since you have seen that A3 is 0, so this result will be again 0. And similarly, A8, you can check it. A8 will be equal to A0 divided by 3 into 4 into 7 into 8, and so on. In this manner, we can get the values of the different coefficients. And so now we will substitute these values which we have obtained here in the equation 2, and after substituting these values in equation 2, we will get the general solution of that equation. So substituting the values of different coefficient, AIs, you can say, in equation 2 we get. In fact, you can see it easily when what is this equation 2? Y is equal to A0 plus A1x plus A2x square plus A3x cube, and so on. So if you will substitute these values, you will find that this is A0 into 1 minus x4 divided by 3 into 4 plus x8 divided by 3 into 4 into 7 into 8 minus so on. And now take A1 as a common factor, then there will be x minus x to the power 5 by 4 into 5 plus x to the power 9 over 4 into 5 into 8 into 9 and minus so on. You can check it. And so this is actually the general series solution of that given equation. So I hope after these two examples, the idea of solution of differential equation of second order with variable coefficient when x equal to 0 is an ordinary point of that equation definitely has been clear to you. So adopting this technique and this method of solution, you can go through your textbook and solve so many problems related to this, and you will definitely find no problem in solving those problems.